My name is Kevin Greer, and I lead the phone team at Google. I'd like to give a little history lesson. So, the second largest engineering project of the 60s um, was IBM System 360. The largest, of course, was putting a man on the moon. So, it was thought that really creating a new operating system was like a mammoth, um, engineering undertaking. So, really, to compete with that, they created an operating system called Multics, and this really required the combined forces of MIT, AT&T, which was the largest communication company at the time, and General Electric, which was the largest company of any type at the time. So these three companies combined to create this new operating system called Multics. And so what we're showing in this diagram is the little blue dots represent the Multics developers, and they're running around and they're going to write code, code is in green. And this square represents the operating system. So along this axis, we have the different types of data an operating system would need: users, groups, processes, devices, etc. And then across the top, we have the features that each of those that you would need for each of that type of data: sorting, search, paging, whatnot. So the way it was written at the time, each of these commands had each of these features, and you would write it each feature for each command. Now, at AT&T in the basement on some obsolete hardware, two guys, Ken Thompson and Dennis Ritchie, were making a kind of toy operating system called Unix, and its name is really a play on of Multics. Okay, and so let's start this up. Okay, well, what's different about Unix is that they didn't implement all these features for every type of data. They implemented each one only once because Unix had the pipe command. So you could take ls or ps, and then you could pipe it into sort, into grep, into more, and then they only had to write these features once. So we can see the Unix developers are not running around coding up the area, they're coding the perimeter. And then these can be reused for every type of data. Now, just as the way we analyze computers running algorithms or data structures and talk about the runtime efficiency or the scalability of those algorithms, we can use the same mathematics for humans running an architecture or a paradigm. So what we're doing is we're graphing here the lines of code, and you can see that since there are 50 times as many Multics developers, their lines of code are increasing much faster, and we can increase the utility. And the Multics utility is linear, so for every line of code that they write, they get 1 unit of utility. But look what's happening with the shape of the Unix utility. It's actually curving up. This is exponential, because once they write one feature, they get the utility of that feature for all of the types of data, not just for one. Okay, and so as they go, they become more and more efficient, whereas the Multics is flat. Okay. So this is kind of like one of the most unbelievable things in the history of computing, is that basically a couple guys in the basement on obsolete hardware did the software equivalent of, going to the moon, like proverbial moonshot, and they did it with dramatically fewer developers. But we can see at this point the utility of Unix is actually surpassing Multics. So although Multics had all the money, all the developers, and all the political support, what it didn't have was mathematics. Mathematics was on Unix's side. So Unix was really sort of mathematically ordained to succeed, despite everything else. Also, because you have much better reuse, it's much more efficient. So the PDP-7 that Unix was written on had 32 times less memory than the large Honeywell systems needed to run Multics. But another thing they did that was controversial at the time was they wrote Unix in a high-level language, for the time anyway, which was C, whereas it was thought that operating systems needed to be written in the low-level assembler of the target hardware to get the optimal performance. But then when new hardware came along, because Unix was written in C, they could quickly port the operating system to that hardware. And at this point, the efficiency of Unix jumps from n squared to n cubed. And this continues right up to the current day with iOS, OS X, Android, Chrome, Linux, all being Unix or Unix derivatives. Okay. And when we talk about foam being feature oriented, that's the same thing that made Unix efficient. So these are all features across the top, right? And you only have to write those once. But when we moved, so this was great when we were command line, but when we moved to GUIs and then to the web, we lost this exponential efficiency. And what foam is really trying to do is bring it back. So how does this apply to Google? So if we take the same kind of grid, Google also started as two developers, let's say Larry and Sergey, with one type of data, web pages, and one feature, which is search. Later, we added ads, and then we started to add more type of data, and then more features. And then we started adding more platforms, just like Unix. So if you look at the um, Google mission statement, to organize the world information, that's this column, and make it universally accessible, that's the z-axis, and useful. The uses are the features. So you can see Google's mission is exactly aligned with this cube. And so what really Google is trying to do is create an operating system for the world's information. Yeah, maybe ad funded and with unusually good search and heterogeneous, but essentially an operating system. And these are all the Googlers running around, writing each feature uh, independently for each type of data on each platform. But this is the Multics model, right? And you're trying to solve what's a cube problem with a linear solution, and that's not really going to work out well. But if we can get those developers to move from coding the volume of this problem space to coding the perimeter, like they did with Unix, then would become exponentially more efficient, and that would really allow Google to much better achieve its goal.